Welcome to week 5 of the 2021 QMC PAC workshop. My name is Joshua Townsend, and today my goal is to tell you a little bit about how to do meaningful calculations on solids. So if you haven't already, let me remind you to go check out the GitHub website, the GitHub repo, with the link right here. And be sure to do a git pull. That way you can get access to these slides as well as the workshop materials and the hands-on portion of the tutorial that we'll be working on after the talk is over. And you can find everything there from all the weeks as well. So if you haven't yet gotten your hands on those materials, be sure to do that. All right, so as I said, today the goal is to highlight for you, make you aware of sort of the most important things to think about when you set out to do a QMC study on a solid of some sort. And to my mind, there are really 3 main topics to discuss. The first are the unique boundary conditions we use when describing a solid within quantum Monte Carlo, and the importance of what we call twist averaging. After that, I'll discuss a little bit about some of the unique considerations for constructing many-body wave functions for solids. In many respects, they overlap very much with what you learned about in week 4 for molecules, but there are a few unique tweaks for solids. And then we'll discuss finite size effects. What are they? Where do they come from? How to quantify them and how to mitigate them. And then we'll turn our attention towards the hands-on portion of the workshop, which can hopefully be a little more interactive. So as Paul said, please feel free to type any questions you might have in the chat. There will be breaks for questions here and there. I can't see the chat, so I apologize. I'll be oblivious and yapping away. So if there's anything important, please, Paul, don't hesitate to pipe in. All right, unfortunately, the 3 things I listed are not the only things you need to know about to do meaningful calculations on solids. And I just don't have time today to discuss absolutely everything you need to know to do meaningful calculations. But the good news is that much of the things you do need to know have been covered already by my colleagues or will be covered in subsequent weeks of the workshop. So for example, I'm not going to discuss things like equilibration of QMC results. That's just as important for solids as it is in any other problem. That was covered by my colleague Jaron Krogel in week 3 on the nexus and statistical analysis tutorial. I'm also not going to discuss DMC time step extrapolation or population bias. Both of those topics were covered in week 4 for molecules by Anwar Benali. Just as important for solids, same exact problem. So I didn't see the value in going over that twice. I'm also not going to discuss what's called mixed estimator bias. That's a somewhat subtle point that you need to know about to analyze certain QMC observables or estimators. And that's going to be covered next week by my colleague Chandler Bennett. So please stay tuned for that presentation because that's an important point in analyzing the results of a QMC calculation. I'm also not going to discuss pseudopotentials. That's going to be covered next week as well by Professor Luboš Mitas. And I'm also not going to discuss spins and magnetism in any detail. That could be a talk unto itself. And that will be discussed in part by my colleague Cody Melton, who is going to present for you a tutorial on spin orbit coupling in QMC PAC. And then finally, I'm not going to discuss systematic improvability of the wave function. That's because it was already covered for the molecular systems in week 4 by Anwar Benali. And many of the ideas, many of the wave function forms that you use to make a systematically improvable wave function in a molecular system carry over directly to a wave function used to describe a solid. And also it's hard to do, systematically improvable calculations on a laptop for a solid because typically when we're doing calculations on solids, we're thinking about supercells and maybe hundreds of electrons or something like that. And many of the more advanced wave function types scale very unfavorably. And so it's difficult to do meaningful calculations on solids of that kind on a laptop anyways. You can certainly do them on big computers at maybe your home institution. So if any of these topics really interest you, or if these are the things you really wanted to learn more about, please don't hesitate to ask, either in the workshop Slack or on the QMC Pack Slack as well. People are very happy and willing to help point you in the right direction and discuss any of these points. It's just, we don't have time to go over everything. All right, with that said, let's get into the first topic, which are the boundary conditions we use to describe wave functions for solids and the importance of what we call twist averaging. All right, so I'm sure that many of you come from a background of quantum chemistry, and in a typical quantum chemistry problem, you use what are called open boundary conditions. Open boundary conditions just mean that you make the assumption that the wave function goes to zero as any of the electrons goes out to infinity, right, in any direction. So maybe, you might think, well, if I want to do a solid, all I'll do is set up a unit cell in this huge vacuum, right? And then I'll calculate the total energy, and I'll make a bigger unit cell, and I'll do the same calculation. I'll look at the total energy per atom, and I'll do a bigger unit cell, and I'll look at the total energy per atom. But the problem is that right at that interface between where the vacuum is and the edge of your little cell, crystal cell that you're simulating, is a very different electronic environment than the deep interior of that crystal, the bulk of that crystal. And these so-called surface effects mean that the convergence of, for example, the energy per atom is very, very, very slow. And what that means in practice is that you would need a very large supercell in order to get accurate bulk properties in open boundary conditions. And so when we do calculations on solids, this is true for DFT as well as QMC, we use what are called twisted boundary conditions, or maybe I should say periodic boundary conditions. And the idea there is that rather than simulating the whole universe and assuming that the wave function goes to zero at infinity, we simulate a very small region of space, and we impose a boundary condition on that region of space that we simulate, such that if an electron passes through one side of that region of space that we're simulating, which we call a supercell, it's instantaneously reflected back to the other side of the cell, and the wave function picks up a phase. Doing this eliminates surfaces. By imposing this periodicity constraint, we're essentially constructing an infinite lattice of cells that are stacked in all directions in space. And so this eliminates surfaces from the problem, which means we don't have surface effects. And as a result, we need fewer atoms to get reliable estimates of bulk properties, which are typically what we care about when we do calculations on solids. But because we truncate the region of space that we simulate, because we are restricting ourselves to simulating only a relatively small region of space, that means we have to be a little careful about how we handle things like long-range interactions. For example, the Coulomb interaction between two electrons, which goes like 1/r in 3D. So as I said, we use in quantum Monte Carlo what are called twist averaged boundary conditions. And essentially you can think about this like the many-body version of Bloch's theorem. So in Bloch's theorem, you have some one particle wave function, and if you have some potential with that's periodic, you can write down that wave function as a little piece that's periodic times a complex phase. And in quantum Monte Carlo, we're doing a many-body calculation. So we have a many-body wave function, psi, which depends on many degrees of freedom. And the many-body version of Bloch's theorem just says that as any of those degrees of freedom goes through one of the faces of your simulation cell, the entire many-body wave function picks up a complex phase. And it looks like e to the I L dot k, where L is sort of the size of the cell that you're calculating. And so this number L dot k, which we might call theta, looks like an angle. And so we call that the twist angle. So in this talk, I'll say words like twist, twist angle, twist grid, k point. These all kind of are referring to the same concept, which is this little piece of the wave function out front that you pick up when an electron wraps around the cell. You may be familiar already if you're doing DFT calculations with PBCs. And in general, if theta equals 0, or I guess in particular, theta equals 0, that's sort of what you would call, I think they call those Born-von Karman boundary conditions, periodic boundary conditions, right? So you get, the wave function is exactly the same as you wrap an electron around. And so twist average boundary conditions is just like the many body version of Brion's own integration. And the importance of twist averaging is that it reduces finite size effects. We'll discuss more about this later. And as a result, you get a much faster convergence to the thermodynamic limit for most of the properties you care about. But I'm thinking in particular of the energy per atom. In this figure on the right, which comes from a classic paper from Lin and Sepperly in 2001, kind of gives you the picture. This is kind of how I think of twist averaging, is this little picture here. So what you're looking at is a 2D slice of K-space for a system. I can't remember what the system is, but it doesn't matter. And you see this large circle here. I guess I have a highlighter, so I should use it. You see this large circle here. That represents the Fermi surface for this system. And then you see the filled in circles, which represent the occupied states in this system. And you notice that those set of filled circles do not well represent that Fermi surface, or that region inscribed by the circle representing the Fermi surface. And so the effect of twist averaging is to move those sets of points around in K-space slightly. That's the effect of the twist, is to perturb those points and to translate them around a little bit. You can see that by the triangles, right? So the circles, the filled circles in this figure represent theta equals 0. And then if you have theta not equal 0, then you get this filled set of triangles. And notice that you fill different states, and the little region of K-space that you fill out is slightly different as well. And so each of these choices of theta, each of these twists, is like its own little independent system. It's a different boundary condition that we impose on the many body wave function. And so we're averaging over boundary conditions when we do this calculation. And so this is the sense in which you're getting the reduction in finite size effects, right? You're filling out this little region of K-space more completely. Okay. Slide not advancing. There we go. So what is twist averaging for? Well, in practice, you should plan to twist average basically all the observables that you calculate, not just the energy. So for a general twist averaged estimate of some property you care about, A, that looks like just a normal average over your estimate, your QMC estimate of A at a particular twist, right? So this is about as easy as you could imagine. There's nothing more complicated here in the analysis to do a twist average calculation than to just analyze anything at a single twist, right? You're just taking averages. And so here, this bracket A is your QMC twist averaged estimate of A, and that's just an average over each value of A that you get per twist. And W here is the corresponding weight. So think about like a K-point mesh in DFT, right? You do a calculation in DFT with K-points and some mesh. If you use symmetry operations, then the weights on those K-points are not equal. And so we can do something very similar in QMC, right? So this is the main idea of twist averaging. Very easy to do in practice. Now, the good news is that these twists are independent. As I said, the twist is like a boundary condition on the wave function. And so two wave functions with two different boundary conditions don't really know anything about one another, right? And what that means is that you can run these guys in parallel, which is great. And because they're independent, you get an error bar reduction that goes like 1 over the square root of the number of twists. So what I'm showing on the right-hand side of this slide is an example of converging the number of twists required to get a robust estimate at the VMC level of the total energy of a 4-atom primitive cell of iron oxide, a 4-atom antiferromagnetic primitive cell of iron oxide. And on the y-axis, you can see the VMC energy, and on the x-axis, you can see I'm changing the number of twists. And as you move from the left to the right-hand side of this figure, you see not only does the energy decrease at first and then kind of fluctuate about some value, but the error bar also decreases as you move to the right. That's not because the calculation with 64 twists was a larger calculation in the sense that each twist was run for longer. It's just that there are more twists. And so because of that, you get an error bar reduction. Now, how many twists are enough? Well, this is one of the first things you need to check when you do a calculation. It will depend on the size of the cell that you're studying, and it will depend on whether the system is a metal or an insulator. If it's a metal that you will need to do twist averaging, probably you'll need a fairly large number of twists. Not thinking about the size for a moment, you will need more twists for a metal than you will for an insulator. And the point I want to hammer home for you is that you got to check this yourself. So just like you do with DFT, you calculate the energy and you change the K-point grid to make sure that you can converge things, and you check the pressure and all of that. It's the same deal in QMC. You have a twist grid and you do a calculation of the total energy, and then you change the grid and you look at the convergence of that total energy, and then you figure out how many you need. Now, the upshot of all this is that Nexus can do a lot of the heavy lifting for you. We'll see this later in the tutorial, but Nexus can generate mappings between calculations using K-points in a primitive cell to twist grids in a supercell. And so much of this heavy lifting, as I said, is done for you. And effectively, this is something like 3 lines of Python in order to do this kind of thing. And I'll revisit that in the hands-on portion of this tutorial later. All right, now in the discussion of twist averaging so far, I've sort of been hinting that everything is the same for each of these twists, except the little boundary condition, right? Except the twist angle. But in a metal, the number of occupied states, of course, depends on K due to band crossings on the Fermi surface, across the Fermi surface. And so in canonical twist average boundary conditions, which is what I've been talking about so far, we're kind of assuming that the number of particles is the same for all the twists, and all that's changing is the twist angle. But there's another technique I wanted to highlight for you called grand canonical twist averaging, in which you allow the number of electrons to vary with the twist. And as I said, this can be important for metals. And what this gives you are smaller one-body finite size effects, but just a caveat that it's not always clear how to choose the number of particles for a particular twist in practice. And if you're interested in learning more about this technique, I would point you towards a number of very good papers. Of course, the Linen Separately 2001 paper is the classic on twist averaging. More recently, there's a very nice paper by Azadi and folks in 2019 that had a very clever scheme of choosing n as a function of the twist using DFT. And another excellent recent example of grand canonical calculations in QMC was by Paul Yang last year in PRB, in which he studied the momentum distribution in grand canonical and canonical twist averaged boundary conditions. And you can see the difference in the momentum distribution shown here. You see in the canonical calculation, you have these finite size effects and this kind of jagged, rough surface on the momentum distribution. But in grand canonical grand canonical twist average boundary conditions, you have this very smooth momentum distribution, just like you would expect. And so how big are these fluctuations? You might wonder, how important is this really? Well, here, for example, on the top, I'm showing the variation in the number of particles, number of electrons, as a function of twist for a 32 atom aluminum primitive, or a supercell, pardon me. And you can see that the fluctuations here are on the order of like a couple percent, 5%, something like that, 7%, I guess, in the extreme case. So it's not nothing, right? This can be important to take care of, but just be aware that this problem of how to choose a number of particles is not always clear. So think a little bit before, burning down 100 million CPU hours on your favorite cluster. All right, so that's all I wanted to mention about the boundary conditions on the wave function. I also mentioned that because we're truncating space, the Ewald, or the Coulomb interaction has to be handled carefully because it's long ranged, right? And this should be familiar to many of you. We use a technique called Ewald summation. This is the same technique that people use when they do molecular dynamics, and the same technique that they use when you do a DFT calculation. So if you're coming from the world of VASP calculations or espresso calculations or some other plane wave DFT code or molecular dynamics code, this should be very familiar to you, right? The main problem is, how do you calculate the Coulomb interaction between a particle in your cell and infinitely many copies of the electrons that are generated due to the periodicity? And of course, that's conditionally convergent. And so the Ewald sum technique provides a rigorous value by breaking up the raw 1/r interaction into absolutely convergent, short-ranged real space term and a long-ranged k-space term here. And so that's all I'm showing in these three figures here. On the left, you can see the raw Coulomb potential, and you can see at the edge of my cell here, it's not equal to 0. And you can do this breakup into this very short-range real space piece, which goes to 0 very quickly. And similarly, a long-ranged piece, which also goes to 0 very quickly for large k, which is short range. So we do the same thing. As I said, this is not unique to QMC. People do this for molecular dynamics and for DFT. But the difference is that in a quantum Monte Carlo calculation, we do Ewald sums a lot, many, many, many Ewald sums. So let's say you wanted to do a QMC calculation on a box containing 100 electrons, all right? A modest QMC calculation on that system would maybe have 1,000 Walkers. Maybe you want to take 1,000 steps, right? This is not a particularly large calculation, but just to paint a picture. How many Ewald calculations does that require? Well, for each Monte Carlo step, you're going to propose a move for all 100 of those electrons. For each proposed move, you got to evaluate 100 Ewald sums in order to evaluate the Coulomb interaction between your electron, which you've just moved, and all the others. You've got something like 1,000 Walkers doing all of this at the same time. And each of those Walkers is going to move 1,000 times. So that's something like 10 to the 10 Ewald sums over the course of this particular calculation. So we do this quite a lot. This takes a lot of effort. And so because of that, QMC Pack uses what's called an optimized breakup, which maximizes the speed and minimizes the error of this Ewald sum. And it's controlled by this parameter in the input called LR_dim_cutoff. And this turns out to be a sort of innocuous looking flag that matters very much for a particular estimator that is used to do potential energy corrections. And we'll return to that in the hands-on portion of the tutorial, or I should say later in the tutorial. And all I want to mention is that this breakup is checked before the calculation starts. So QMC Pack will look at what you're trying to do. It'll do an optimized breakup, and then it does a little test to make sure that the optimized breakup is accurate and gives results that are within an acceptable tolerance with respect to the standard Ewald. If you're interested in reading more about this, you can find that in a classic paper by Natoli and Separately from 1995, linked down here. So that's all I wanted to say about the boundary conditions on the wave function, as well as twist averaging. And I think we'll take a QA break. So Paul, are there any questions?
Thanks, Josh. So I don't see any questions yet, or give people a moment to type any that they wish. But I do have one question on twist averaging. So you pointed out some similarities to K-points that we're all familiar with from DFT and mean field calculations. So are the K-point densities and the grids we might use in DFT a sort of a good guide for what we might need in our many body calculations, or do we need more?
Yeah, that's a good question. So what you mean is, if you have say you do a DFT calculation in your favorite 4-atom cell, and you figure out how many K points you need in the DFT calculation, does that tell you how many K points you would need in the corresponding QMC calculation? Is that what you're asking?
Exactly.
Yeah, I would say that I don't know, because typically what I like to do is I do a very small DFT calculation with lots of K points, and then I make a big supercell in QMC. And so of course, you're rarely doing the same problem in both, but It also would depend on the quality of the orbitals that you're using to do the DFT calculation and how good those are in the corresponding QMC calculation. For example, you could think of something like FeO, right? If you're doing a PBE calculation on pure iron oxide with DFT, you would predict that to be a metal. And so in your DFT calculation, you might need a lot of K points in order to get a well-converged value for the energy. That's not because FeO in real life is a metal. It's because that's a deficiency of PBE, right? And so in the corresponding QMC calculation, you can gussy things up enough to sort of wiggle your way around this particular problem. But it's the sort of thing that you wouldn't want to bet your life on. So I think as a matter of practical guidance, what I would recommend is that you should test both. You should test your DFT calculation, and then you should construct your QMC cell, and you should scan K points. Now, I should say, you could totally do that in a small QMC cell, and then look at how many K points you need for a particular number of atoms, and then you can scale that within QMC, right?
Thanks, Josh. So we do have one question from Igor Evangelista. Is QMC pack, or maybe Nexus, able to pick the symmetry of the problem to reduce the number of twists?
Nexus can do that, yes. QMC pack, to the best of my knowledge, doesn't know much about symmetry, but Nexus does know quite a bit about symmetry, and that'll be one of the components of the hands-on tutorial today, is using Nexus and symmetry operations to reduce the number of K points required to achieve a certain a certain kind of calculation.
But one more question, and I think we can continue. So this is from Kamal Chaudhry. Is twist-based energy convergence good enough to ensure convergence on electronic properties such as the band gap?
Ooh.
So I guess the question is about convergence of properties other than the total energy.
Yeah, that's a good question. The best thing to do is to check. My typical MO is to do convergence on the total energy because that's the cheapest thing to do, right? And then I always go a little bit more, right? Because I'm always worried about exactly that problem. So if it's something that the band gap is like especially pernicious, though. So that's kind of an especially pathological example. But yeah, I mean, again, testing is your friend here. Do tests. And again, you can do these in small cells, right? So you don't have to burn down an entire forest worth of power here in order to get your twist grid converged. You can do this in a modest cell. Band gap's a bad example for that, but for example, the spin density, you can do that in a modest cell and then scale that right into a supercell that you really care about. So when in doubt, test is what I would say generally.
Thanks, Josh. There's a couple of other questions which I'll answer in the chat. I think we can continue.
Okie dokie. All right, so next up, let's discuss some of the unique aspects of many body wave functions for solids. All right, so as with molecules, the Slater-Jastrow wave function is the simplest, the most compact, and the most common many-body wave function ansatz that we use in QMC pack. And it looks like this. It looks like a Jastrow factor, e to the j, which depends on some degrees of freedom of your system, and a Slater determinant, which is composed of what we call single particle orbitals. Those are those phi objects. These are the eigenfunctions, if you want to call them, from DFT, or orbitals coming from DFT typically. And the advantage of this wave function is that through the Jastrow factor, we can explicitly incorporate electron correlation. So the thing I want to highlight for you is that the determinant piece of this wave function comes from outside of QMC. Today in the tutorial, we'll be using Quantum Espresso, which is a DFT code, to generate these orbitals with which we will populate a Slater determinant. And then you slap a Jastrow onto your wave function, and then you optimize that Jastrow within QMC. So the determinantal part of the calculation of the wave function, comes from outside QMC, typically from a lower level theory. And the Jastrow portion of the wave function comes from inside of QMC and is constructed entirely with QMC. All right, now what are these Jastrows doing? It's important to know what the Jastrows can do for you, and it's important to know what the Jastrows can't do for you. So roughly speaking, the Jastrows that I'll talk about today and the Jastrows that I would say are sort of most important for calculations on solids are 1, 2, and 3 body Jastrows. These are splined, cubic splined Jastrows. In the case of a 1 body Jastrow, this is between, this encodes correlations between an electron and an atomic nucleus. The 2 body Jastrow, which is by far the most important in terms of its improvement to the many body wave function, encodes for correlations between pairs of electrons. And importantly, this encodes for correlations between pairs of electrons of unlike spin. Right, so many of you will know that in Hartree-Fock, electrons of opposite spin are totally uncorrelated, and that's unphysical, right? And so this 2 body Jastrow helps patch up that deficiency. And finally, the 3 body Jastrow, which can be important for deep semi-core states. If you've got a big honkin' pseudopotential, you know, if you want to do gold and you have a really, really deep semi-core states in your pseudopotential, this 3 body Jastrow term can be quite useful. It encodes for correlations between pairs of electrons and an atomic nucleus. And this tends to be a fairly short-ranged Jastrow. The 1 and 2 body Jastrows tend to be long-ranged, and the 3 body Jastrow tends to be relatively shorter ranged. And then unique to solids, we have what's called a K-space Jastrow. So this is sort of only used inside periodic boundary conditions. And what it does is restores the long-range correlations to J2. We'll return to this later on in the tutorial, but roughly speaking, when we make these splined Jastrows, we have to enforce that the Jastrow goes to 0 at the cell boundary or the Wigner-Seitz radius. And because of that, electrons beyond a certain length are completely uncorrelated. And of course, we could patch that in by adding in a long-ranged only piece, and that's this K-space Jastrow. And so this can be important in modest, small to modest supercells for QMC, and it becomes less important as the size of the supercell you're doing simulations on increases. And that's because as the cell increases, the real space 2 body Jastrow can pick up more and more and more of that long-ranged correlation. So you can see there's a trade-off. And then finally, I just want to stress that the nodes of the quantum of the many-body wave function, are not affected by these Jastrows, only the amplitude of psi. So all the Jastrow does is squash or stretch psi vertically. It doesn't change the points along which psi is 0. And so because of that, as you saw last week in the tutorial on molecules, the DMC energy is frequently unaffected. For practical purposes, is unaffected by the Jastrow, but the efficiency with which you sample, it goes way, way, way up. So it's always worth it to run with a Jastrow. And for other observables, of course, these Jastrows make a heck of a difference, right? So if you want to sample something else, like the spin density, for example, then these Jastrows are also important. So from a practical standpoint, you should always plan to run with Jastrows. And I would say at a minimum, you should be running with 1 and 2 body Jastrows. And we'll return to that in the hands-on portion of this tutorial. All right, so I wanted to just say, I guess, one more word about this long-range piece of the Jastrow, right? So you know how we have to do Ewald to take care of the Coulomb interaction between electrons because of the periodicity. Well, turns out that the correlation of the 2 body Jastrow kind of looks like a 1/r type thing as well. And the real space portion of the 2 body Jastrow is kind of like the Ewald, the short-ranged real space piece of the Ewald term. And so this K-space guy you can think about as adding in that long-range contribution to the Ewald sum. And so this thing, U of K, is the K-space Jastrow. It's defined purely in K-space. And what I'm showing on the right-hand side of this figure is an example of what that 2 body Jastrow looks like and the corresponding K-space piece. So on the x-axis of this figure on the right, I'm showing the magnitude of K. So this is like, you know, the length of a K vector here. And then on the y-axis, I'm showing the value of the Jastrow coefficients. This top solid curve here represents the complete two-body Jastrow. That's the Fourier transform of the real space piece plus the direct K-space piece. And I'm doing that for three system sizes: a 32 atom cell of aluminum, a 108 atom cell of aluminum, and a 256 atom cell of aluminum. And you can see that as the cell size gets bigger, you get further and further and further, longer and longer range, which means smaller and smaller K. So you move left on this figure as you increase the cell size. And you can see this is like a classic 1 over R behavior, right? This looks like 1 over K squared, right? Which is the Fourier transform of 1 over R. And these broken curves down here are the K-space only pieces. And what I want to highlight for you is that the K-space piece, the direct K-space piece for the 256 atom aluminum cell is much smaller in amplitude than the corresponding K-space Jastrow for the smaller 32 atom cell. So that's just what I was saying. As the cell size gets bigger, the real space Jastrow can pick up more and more and more of the long range correlation. And so this K-space Jastrow becomes more important for small to medium size cells. Okay, now how about the determinantal part of the wave function that we use? Well, as I said, we use DFT, and today we'll be using quantum espresso to construct the phis, the orbitals, what we call the single particle orbitals that we use to populate the Slater determinant. And in a code like espresso or VASP or many other plane wave DFT codes, these phis are represented in a plane wave basis, right? So you have some e to the I kx thing, and then you have some coefficients, and you get a linear combination of those to represent a general phi here, a general orbital. How many of these plane waves are there? Well, in a typical DFT calculation, there's something like a couple thousand, maybe say 10,000 plane waves per orbital. So if we were to use this basis to represent each of these orbitals, then every time we moved an electron, we'd have to calculate like 10,000 numbers, right? We have to do 10,000 calls to sine and cosine, right? And so that adds up very quickly, right? I mean, this is a huge number of sine and cosine calculations just to get the value of the wave function at a single point, right? And then you're going to do this for a number of moves and a number of walkers, and it's going to be a real pain in the butt, and it's going to take a very long time. So we don't do that. What we do is we use B-splines, 3D cubic B-splines, to represent each orbital directly in real space, right? And doing this reduces the number of numbers you need to calculate in order to get the value of the wave function at a certain point from something like 10,000 down to 64 grid points per orbital. And doing this is independent of system size, and it's independent of the underlying DFT basis set size. So this is an incredible performance gain for us, because now instead of sitting there calculating 10,000 sines and cosines in order to figure out the value of some single particle orbital, now we just look up 64 numbers, right? Or we calculate 64 numbers to get the value of a single particle orbital at a point in three-dimensional space. And this is done for you automatically inside QMC pack. So the way that the workflow will go, as we will see later in the tutorial, is you do a DFT calculation, you write a wave function file, which is, has a suffix of H5. It's an HDF5 file, pardon me. And inside that HDF5 file are all of the coefficients on the plane wave basis to represent all of the orbitals that you care about. You point QMC pack to that wave function, and then when QMC pack starts up, it reads in all those coefficients. It splines all of the orbitals for you, and then tosses out the coefficients, and then all you carry around are those splines, right? And then this is very efficient, very fast, and done automatically for you. So it's essentially totally hands-off. Now, as I said, when we do calculations on solids, we typically want to do relatively large calculations, at least as compared to molecules, right? We want to do 100 atoms. I showed on the previous slide aluminum, a 256 atom aluminum supercell, right? And so the wave functions that we use for solids can really take up quite a bit of memory. And one way that we can reduce the memory footprint of these wave functions is to use what we call hybrid representation. And the idea is kind of like an LAPW sort of approach, right? Is you represent the splined wave functions rather than on a rectilinear 3D mesh in all of space. You instead apply a transformation in which you represent the highly oscillatory region of the wave functions near the nucleus with YLMs, with spherical harmonics times a radial spline. And then you have a relatively coarser rectilinear mesh in the interstitial regions between atoms. And so that's shown schematically here. So here you have a relatively dense rectilinear mesh and you apply a transformation. You have these spherical regions about the atom centers. Then you have an interpolation region between this coarse rectilinear mesh and the spherical region. And doing this can give you a very substantial memory reduction. Something like 4 to 8x is possible. And that's controlled by the hybrid rep tag. And in the hands-on portion of the tutorial today, we'll see how to do that. There are a couple parameters that you need to converge in order to do this well. And as you might suspect, that's the number of YLMs to include, how big should the spline be, such and such. And so there are a few examples in the tutorial that you can work through to look at how that transformation works, and you can see some of the wave see some of the memory savings that you gain by applying this transformation. In the tutorial materials, it's not much, right? Because it's a relatively small supercell, but this can really help you out when you want to run in a larger cell. All right, now the final trick we have for reducing memory footprints, and I believe someone was asking about this just a few minutes ago, is we can use symmetry to reduce the number of K points required to represent a system that we care about, right? So as you know, in DFT, you can do a 3x3 K point mesh on a 1x1x1 cell. That should give you the same energy as a 3x3x3 supercell on a 1x1x1 K point mesh, right? And so there's a correspondence between cell size and K-point meshes. And we can exploit this, right? If we know that we want to do a QMC simulation on a 3x3x3 supercell, well, then we can use K-points in our 1x1x1 unit cell or primitive cell to reduce the amount of memory required to store that corresponding wave function for the supercell. And this basically just comes down to straight up Bloch's theorem. And again, Nexus knows how to do this for you. You can see in the tutorial how we do this. And I would encourage you to experiment with this because it's like literally 3 lines of Python. You can say, give me the best supercell that is composed of 32 atoms, and I want a 3x3x3 K-point grid with a shift in that supercell, and Nexus will say, here are all the K points you need in your primitive cell in order to generate that supercell. So that's done with what we call a tile matrix. And using Nexus, you can sort of look and see how that's done in detail. And I'll show you where to look in the QMC pack input to see how that's done as well. All right, so that's all I wanted to mention about the many-body wave function. Are there any questions at this point?
There aren't any that we haven't answered yet. Let's just give people a moment to type or even put a quick word in to say that they're typing. So we've got one question from Adam Denchfield. Mm-hmm. What's special about B-splines?
Not much. I mean, they're pretty handy objects that are used for lots of different problems, but there's nothing special about B-splines in terms of QMC. They're just an especially compact and very amenable to representing wave functions compactly. I think that's all.
All right, no other questions?
Okay, great. Okay, in that case, we'll move on to finite size effects. And this is sort of one of the sort of most unique aspects of doing calculations on solids is consideration of finite size effects. Okay, so what are finite size effects? Finite size effects, finite size errors arise because of this trick that we're playing. We're using periodic boundary conditions, which means we don't simulate the whole universe. We simulate a little teeny tiny box, and then we replicate it in infinitely in all three directions in infinite extent. And because we do this, space is restricted. And that restriction means that there is an error that we incur in pretty much all of the outputs that we calculate for a solid, right? The way I like to think of this is like a discrete versus a continuous set of points in a Brillouin zone for a finite cell, right? So you can calculate the energy per particle in a one-body theory by doing an integral over the Brillouin zone, right? And then when you do your actual DFT calculation on a computer, you can't hold infinitely many K points in memory, and so you use a discrete mesh and you make the mesh big enough, and things seem to work out well enough, right? And so it's the same kind of problem in QMC, right? And the point that is really most important for you to understand about finite size effects is that these finite size effects are not due to the fact that there's an error in the wave function. These finite size effects exist even if you knew the exact wave function for the system you wanted to calculate. These errors or these effects arise because of the discretization of space, not because of your ignorance of psi. So basically every QMC output on solids is biased when comparing to experiment. Now that's kind of a scary statement to make. So let me just soften that very slightly by saying how much any particular output is biased depends, of course, on a number of factors, including how large the cell is on which you're doing the calculation, the quality of the orbitals that you're using, the twist averaging scheme, and so on and so forth, right? So it's not that you can't ever compare to experiment, quite the opposite. It's just that you gotta keep these things in mind in order to make meaningful comparisons to experiment. And there are pretty much two ways to get estimates of QMC properties for solids in the thermodynamic limit. One way is to do what we call a thermodynamic extrapolation or extrapolation to the thermodynamic limit. That just means you do a set of QMC calculations over different system sizes. You would do a 32 atom calculation, a 108 atom calculation, a 256 atom calculation, and then you look at the extrapolation as 1 over the number of atoms goes to 0, which means you go off to infinity, right? And you can look at how the energy, for example, changes there. That's pretty expensive because you got to do QMC calculations in very large cells. So the other technique that we employ is to use what are called finite size correction schemes. And that's what I want to discuss with you today. So this figure on the right kind of illustrates what I was just mentioning about how you can do an extrapolation to the thermodynamic limit. What I'm showing on the x-axis of this figure is 1 over the number of atoms, right? So in this figure, points to the left are larger cells, and points to the right are smaller cells. And this teal line you see here, which is labeled uncorrected, is just the raw twist averaged energy per particle that you get from a normal QMC calculation. I haven't done anything special here. There's time step extrapolation, but there's nothing special here. And you get this linear behavior, and you extrapolate out to infinite system size, which is the y-intercept. You get a certain value. The blue line that I'm showing here up top, which is almost flat, are the values of the energy per particle after incorporating finite size correction schemes. And what I want you to notice is that these two lines extrapolate to pretty much the same point. I'm not showing the uncertainties in these lines, so they don't. These two lines don't perfectly intersect, but statistically significantly they intersect. And what this suggests is that it's possible, in this case, to do QMC calculations in a 32 atom cell, apply finite size correction schemes of some flavor that we'll discuss in a bit, and get values for the total energy that are pretty much as good as you could get from doing the full-blown extrapolation. So that's the utility of finite size corrections. And the main idea behind many of these finite size corrections is that in a big enough cell, many of these corrections come down to what's basically an integration area. Throughout this tutorial, we've talked about integrating over the Brillouin zone versus summing over a discrete mesh. That's exactly what most of these finite size correction schemes come down to, is looking at a difference between some quantity integrated over the Brillouin zone versus some quantity sampled over a discrete set of points in the Brillouin zone. And so I would point you towards 3 really must-read papers on the gory details of how these finite size correction schemes work. Let me just say that there are many finite size correction schemes. I'm not going to be able to cover all of them today, but I want to give you at least a sampling and then point you towards these papers by Chiesa et al. In 2006, Drummond et al. 2008, and then Holtzman et al. Most recently in 2016. Who are all kind of doing the same thing, but they make slightly different approximations or slightly different assumptions. And so the spirit of these schemes, the spirit of these finite size correction schemes are all very similar, but the gory details are slightly different. So these are the points where you should really start if you're gonna start to worry about finite size corrections practically. And then I would say if you want some inspiration, or if you want to see some excellent recent applications, I would point you to these 2 papers by Yang et al. Last year in 2020, who did QMC calculations on lithium and did a really fantastic job of discussing and quantifying finite size errors. And then more recently by Ghani Anna Berdiev in PRB, where they looked at thermodynamic extrapolation extrapolation to the thermodynamic limit of silicon. And so have a look at those in order to get started. So first, I want to talk a little bit about potential finite size corrections. And there are a couple sort of built-in corrections to QMC. So I'm going to highlight some of those, and then I'll also discuss, what are the more rigorous finite size correction schemes as well. And those typically require post-processing on the user's part. So the first scheme that I want to discuss is called a model periodic Coulomb. And this is a paper written by our own Paul Kent in 1999. The main idea is that when you do this Ewald breakup, you get the Hartree energy for the system exact, but you get a bias in the exchange correlation energy because there's a spurious correlation that you're introducing when you do this periodic replication of the cell, or the infinite replication of the cell. And so this modified periodic Coulomb term is kind of like a patched up version of Ewald. And the main idea is that you have some, you rewrite the Coulomb interaction as some normal sort of short-ranged Coulomb interaction inside the cell. And then you have a modified potential that you apply for the long-range piece outside of the cell. And QMCPAT can do this for you. This estimator is called MPC in the code. We'll use it today. And you can look in the manual to see some of the details associated with it. And you can read the paper as well to see how, see what the main ideas are. And what I want to highlight is that it's not a quote unquote real finite size correction scheme by itself, but it's frequently used in that way. It's really the correct, or it's an improvement on the potential. It's not really a correction on the potential. It's an improvement of the potential. So you can frequently run with MPC, and it is oftentimes used as a correction to the potential energy, but there's a little bit of subtlety there. Okay, now another scheme that's actually appealing because it's totally external to QMC is what we call the KZK correction. And the idea of the KZK correction is that in a normal DFT calculation, the exchange correlation energy functional that you use is extrapolated to the thermodynamic limit for you. And the KZK correction just says, well, what if we just did a DFT calculation using an exchange correlation functional for that particular number of electrons? So in other words, we don't do the extrapolation to the thermodynamic limit on the properties of the HEG, right? You simulate the HEG with n electrons and take the exchange correlation energy from that. This gives you a correction to one-body finite, what we call one-body, two-body kinetic energy and potential energy corrections. And it's entirely independent of QMC, which is also appealing because it's very fast. And in espresso, it's as simple as doing DFT equals KZK. But beware, it's using LDA, right? So the exchange correlation functional that it uses is LDA. But the advantage is that it's very fast to do. Just be aware that you got to do this in the same supercell in which you're doing your QMC calculation, right? So frequently when we do calculations on solids, we do DFT calculations in a primitive cell. But if you want the KZK correction, you need to do that. You need to do that calculation in the honest to goodness supercell you're running your QMC calculation. And this figure on the right kind of shows how you are correcting DMC energies using this correction. So in black, you have a raw DMC numbers for the energy per atom with respect to some well-converged value in the thermodynamic limit. And in the blue line is this KZK correction. And as you can see, you can run in a much smaller cell and be very close to this value in the thermodynamic limit. It's not perfect, but it is fast. And so in terms of potential finite size corrections, I would say that the gold standard is to use what's called the structure factor, the electron-electron structure factor. And the idea is, as I mentioned before, that these corrections come down to differences between integrals over the irreducible Brillouin zone and a discrete sum over the Brillouin zone. And in the case of the potential energy per particle, you can write that as something like a sum over the structure factor, right? And so this correction involves then the structure factor. This estimator is provided for you in QMC pack. It's called SKAll, and you can use a tool in post-processing called QMC finite size in order to estimate the correction to the potential energy using this estimator. But this has to be done in post-processing. QMC pack will not do this for you. Right, so MPC is just an estimator. You just put that in, and in QMC pack will just give you straight up the MPC energy. So it's as easy as using QMCA to average that. But for SKAll, it takes a bit more work. But it's a more robust estimate of the finite size correction, of the finite size effect. And this figure on the right, I want to highlight and call to your attention the importance of this parameter LRDIM cutoff that I mentioned way in the beginning of this tutorial. This controls how this Ewald breakup is done. This optimized Ewald breakup is done. And by default, the value of LRDIM cutoff, I think, is 15. And what you're looking at on this figure on the right is the structure factor, S of K. So here's S of K on the y-axis. Here's K on the x-axis. And so you see a characteristic S of K coming up here. And with the default LRDIM cutoff, this is in a relatively small supercell, I should say. You see you get this spurious behavior. And that's because of the way the splining of the structure factor is done when you do this finite size correction. And so in a small cell, you may have to increase the value of LRDIM cutoff in order to get the correct physical behavior of the structure factor here when you do the correction. So please be aware of that. If you're running in an absolutely huge supercell, you probably don't need to worry too much about this. But if you're in a small to modest supercell, this is something you'll need to check. All right, so that's most of what I wanted to say about potential energy correction schemes. Again, that's not an exhaustive list, but those are some of the most important correction schemes, and you can consult the literature to learn more about those in detail. Turning our attention to kinetic energy finite size corrections, there's basically two ways to do it. You can either examine the long-range behavior of the two-body JASTRO. This can be done for you by the KE core estimator in QMC pack, but it's not guaranteed to be accurate. You should probably test that. And the other way is to examine the momentum distribution, which is provided for you via the N of K estimator. But again, just as with the SKAll estimator. This must be done in post-processing. So you got to roll your own correction here. And again, I would point you to this recent paper by Paul Yang in 2020, where he worked through both of these kinetic energy correction schemes and a number of potential energy correction schemes. And so this might be a good place for you to start if you're thinking about how to start doing your own calculations on your favorite system. Okay, so as I said, kinetic energy corrections are one of the ways to get a kinetic energy correction is to examine the long-range behavior of the two-body JASTRO. Twist averaging reduces some of the kinetic energy finite size errors, but it's typically not enough unless you're in a really, really, really large cell. Further correction is often needed. And so the way you get that next level of correction is to examine the long-range behavior of the complete two-body JASTRO. That is to say, the Fourier transform of the real space J2 plus the direct K-space piece. And a la Chiesa et al., the correction to the kinetic energy, delta T here in this equation, is just a difference between an integral over the JASTRO and a discrete sum. And to leading order, this just looks like a single term here with A, this number, an adjustable parameter, which is determined from a fit of the long-range behavior of the two-body JASTRO that looks like this. And that's this gray curve here. That is the fit. So that's the thing that we're using for this, this correction scheme here. And so that can be done for you in QMC Pack, although I would just mention one small proviso. The KE core estimator in QMC Pack does not know about the K-space JASTRO. So if you're doing this in a big cell, KE core is probably okay. But if you're going to do this in a very small cell and you're using a K-space JASTRO, it's probably worth checking the correction yourself to make sure that it's reasonably accurate, or to look at the bias that you're inheriting by ignoring the K-space JASTRO. Okay, so as with the potential energy correction scheme, the gold standard kinetic energy correction is to use the momentum distribution. And the reason that's true is because, first of all, it's independent of the JASTRO. And so as you go forward into the future, you could imagine getting to a point where you could really do systematically improvable QMC calculations. And as you may know, if you have a huge multi-determinant expansion, for example, your two-body JASTRO starts to go away, right? Well, that doesn't mean that there's no finite size error anymore. It just means that you don't have a two-body JASTRO anymore. And so you can't rely on these two-body JASTRO schemes to give you good kinetic energy corrections. Or similarly, if you're doing AFQMC where there is no JASTRO, you're kind of out of luck if all you were relying on is the JASTRO-based correction schemes. And so the momentum distribution is sort of the way to go for general wave functions. And again, similarly to the case of the potential energy corrections and the long-range JASTRO corrections, it's just a difference between an integral and a sum, this time over the momentum distribution instead of the JASTRO or the potential energy. Now, there is unfortunately one small proviso that I must mention, which is that the momentum distribution converges to big enough, quote unquote, somewhat slowly. And so shape corrections may also be important, right? This whole difference between integral minus discrete sum trick relies on the assumption that the quantity you care about, say the momentum distribution in this case, in the discrete system you're simulating, is basically of the same shape as the system in the thermodynamic limit, but you're just sampling it incompletely. And the momentum distribution is, unfortunately, converges quite slowly. So that's not always true for the momentum distribution. In fact, I'm showing on the bottom right of this figure, the momentum distribution for the HEG, the homogeneous electron gas, for a number of different system sizes here, number of electrons here. And you can see that even in a relatively large 250 electron cell, you know, the momentum distribution is still changing quite a bit. And again, I would point you to these two papers by Yang et al. In 2020 and by Holtzman et al. In 2011 for the gory details of how to get robust kinetic energy corrections from the momentum distribution. in this case. So sort of the final words I want to say about finite size corrections is that there are many schemes. They all focus, or most focus, on the same quantities: the long-range behavior of the two-body JASTRO, U of k, the structure factor, the electron-electron structure factor, S of k, or the momentum distribution, N of k. QMC Pack provides all of these estimators to you. And some of these, QMC Pack will actually provide you the correction, will provide a correction for you. For example, KE core looks at the long-range behavior of the two-body JASTRO. But it's always up to you to process these estimators correctly and to apply these corrections correctly in post-processing. And many of these schemes make different assumptions, they make different approximations. And so all I can say is that testing is required. And you should plan, when you start a new QMC project, to play around with many of these correction schemes in small and modest supercells. And when in doubt, go to a larger supercell, because this is how you really test these schemes, right? So see if you can design a problem where you can do an extrapolation and then test some of these schemes and see how they do. And that's kind of how you figure out what to do for the big project. So I think in summary, I'd like to leave you with just a checklist of things to keep in mind when you think about designing a study of your favorite solid system using quantum Monte Carlo. You need to converge the grid of twists. And again, that will depend on the system size you care about. It'll depend on metal versus insulator. It'll depend on maybe even the shape of the cell, the quality of the orbitals. Symmetry is your friend. Use Nexus to exploit symmetry as much as possible, because those wave functions for very large supercells get big very fast. And I'll also plan ahead for estimators and observables. None of these estimators are free, which means that you pay time for every estimator that you add. So you could certainly add every estimator in the book, so to speak, but it's going to take an eternity for that calculation to finish. So try to think ahead about what it is you want to know about the system and plan accordingly. It's really a shame when you finish a huge computing campaign only to realize, like, oh, I really needed the momentum distribution in order to do this thing I care about, and I forgot that. Now you got to do everything all over again. And I would also encourage you, as I mentioned several times, to work for as long as possible in a small cell. Things like twist grid convergence can be done in a small cell. And establishing the amount of work required to achieve a desired accuracy can be established in a small cell. So there's a number of QMC calculations that you can do upfront that are relatively cheap, that will help you kind of get the lay of the land and scout out and outline what your project will really look like when you scale up to a larger cell. And you need to plan to quantify or mitigate finite size effects if you want to extrapolate to the thermodynamic limit, or if you want to calculate observables in the thermodynamic limit. And again, when in doubt, get a bigger supercell. And feel free to reach out to the QMC Pack community at the QMC Pack Slack, linked right there, with questions or comments, because people there are very happy to help. And there's a lot of expertise there. So I think with that ends the tutorial component of the talk. So let's stop and take questions, and then we'll turn to the laboratory exercises.
Thanks, Josh. There's no additional questions yet, but we'll give people a minute. Let me just ask one question on the different finite size schemes that you covered. So you pointed to the the use of the structure factor and momentum distribution as seeming to be sort of the long-term route that the community will be using, but I still see a lot of work using some of the earlier approaches. So what are your thoughts on why that is?
Well, it's a heck of a lot easier, first of all. and I suspect that's probably part of it. Also, if you're, you can always run a bigger supercell, right? And so maybe you can get away with not being as careful with your finite size correction schemes if you can afford to just run in a larger cell. Although I would say that Paul Yang's lithium paper was actually very encouraging, because he showed the Chiesa correction as being very favorable, very comparable to the full-blown NFK correction. And so perhaps for some problems, these are just similar enough that you can afford to do the cheap thing, right? But the way to establish that is really by testing, not by just doing the cheap thing and calling it a day, I would say. Okay, great. So today's tutorial is going to be focused on doing some DFT calculations to generate a wave function using espresso. Today we're going to be working on a 2-atom primitive cell diamond, and then doing supercell calculations in QMC. We'll optimize some Jastros. We'll look at some then production QMC calculations in the supercell, and then analyze the results. Okay, so in the script provided for you in the week 5 directory, you should see a Python script called solids_example.py. And so looking in there, you'll see a bunch of Nexus stuff outlining the scope of the calculations and what to do and in what order and so on and so forth. So what I'd like to do is to just step you through what the guts of that script looked like, the most salient features of that script. I'm going to assume that you already know Python, so I'm just going to focus on the Nexus-y bits and the physics-y bits. And I'm happy to take questions on specific details if they come up. Okay, so the first salient piece of this script is to what we call generate the physical system. So here I'm generating an object called prim cell. This is a 2-atom primitive cell, which is this guy right here, 2-atom primitive cell of diamond. And you can see I'm specifying the units in angstroms, and then I'm specifying the lattice parameter here, A, also measured in angstroms. That's about the ambient lattice parameter of diamond. And so here's my primitive cell that I'm constructing, the lattice vectors for the primitive cell. And then I'm populating the internal degrees of freedom. You can see there are 2 carbon atoms that I'm putting in the cell. Here are their fractional coordinates inside the cell. And then here are the pseudopotential. This is the pseudopotential configuration, right? So this is a 4-electron carbon pseudopotential that I'm specifying. Actually, I'm not specifying the pseudopotential. I'm specifying that this thing should have 4 electrons on it, and I'll specify the pseudopotential, pardon me, in a moment. Okay, now as I mentioned, constructing a optimal supercell with a twist grid and all that other stuff is like 3 lines of Python, and so you'll see that inside the script as well. And so from the primitive cell, we construct this object called tiled. Okay, this primcell.structure.tileopt4 means please construct for me the most spherical supercell composed of 4 copies of the primitive cell. That's what this object is. And then you say on the second line, please tell me what K points are required in the primitive cell in order to construct a 2 by 2 by 2 grid of K points with no shift in that supercell. And then finally, we construct this object called supercell, which takes as an input this tiled object, this intermediate tiled object. And again, we have to specify the number of electrons per particle or per atom here. And so if you wanted to, as it's constructed, what I'm doing is constructing an 8-atom supercell, because the primitive cell contains 2 atoms, and I'm asking for 4 copies. So that's 2 times 4 equals 8-atom supercell. And then I'm specifying the K point mesh I want in the supercell. I don't specify anything about the primitive cell. I just say, please give me however many K points and whatever K points those might be, such that when I do the tile into the supercell, I'll have a 2 by 2 by 2 grid. So it's very easy to change the size of the supercell. All I do is change this first line from tile underscore opt 4 to tile underscore opt 64 or 128, or however, whatever you could change it to 5, right? That would be some very strangely shaped supercell, but it could be any integer. And similarly with the K-point grid, you can change that to be whatever you like, 3 by 3, 3 by 3 by 3, whatever you want. You can add a shift, whatever you want. And this will take care of all the internal symmetry operations for you. You can look inside that supercell object. So after you construct the supercell on the third line, you can just do like print supercell right under that. And Nexus will spit out the contents of that object supercell, and you'll see all the stuff that's inside of it. It has a copy of the primitive cell, and it will have a list of all the K points that are required in the primitive cell to tile a supercell of the given size with the given K point mesh you've asked for in the supercell. And so you can look at the guts of the supercell that way. So for now, you should just maybe keep this for the default settings. I guess you could change it if you want. Nexus will do it all automatically for you. So you can play with it if you want, but beware, if you make a big supercell, it's going to totally slag your laptop. So I'm not sure what kind of hardware you might be running on. If you're running on a laptop that doesn't have a lot of cores or a lot of memory, you probably shouldn't push the tile opt above an 8 atom cell. Maybe you could go a little bit more than that, but don't try to do a 100 atom cell on your laptop. And similarly, you could play with the K-point grids, and you can see, how many twists do you get if you ask for a 4 by 4 by 4 K-point grid in a particular supercell. It will depend on the symmetry of the supercell. So if you ask for a supercell which happens to be cubic, for example, the 8 atom supercell happens to be a cubic supercell, you need relatively few K points for a particular mesh size, right? Because you have a lot of symmetry operations. But in general, for an arbitrarily sized supercell, you're going to have some horrible triclinic thing. And so the number of twists that you'll get for say a given K grid size could be very different. So that's something else you should play around with if you're interested in this sort of thing. So I can't see the chat, and I'm not sure exactly how to proceed. My plan was to just kind of give an overview of input and output, and then maybe hang out and take questions. Do you think that's a better way to do things, or should I wait for people to sort of do the steps that I'm just presenting?
Josh, I would simply talk through these steps as you suggested, and we can take any questions at the end. And then as people encounter things later on, we can deal with that on the Slack.
Great. Okay, thanks. I'll do that. All right, so that was step 0. That's how we tell Nexus, please, I want to study diamond. Here's how big the cell is. I want to make a particular kind of a supercell, and I want a particular grid of K points in that supercell. Please do all the dirty work for me. And Nexus is happy to do that. Now we do our first real quote unquote calculation, which is the DFT calculation to generate a well-converged electronic density, from which we will then compute in a subsequent step the single particle orbitals, right? The orbitals that we want to fill up the determinant in the supercell. And so, as I said, that's kind of a 2-step or a multi-step process. The first step here is to do an SCF calculation. So notice that the first calculation that we do is an SCF calculation, a full-blown single-shot DFT calculation. We're using PBE, and we're going to do that calculation on the primitive cell, in the 2-atom primitive cell. And then here's some pseudopotential information that Nexus cares about. And then finally, look at the K-point grid. This is a very large grid of K points that I'm using in the primitive cell. All right, doing it this way, first of all, is a very cheap DFT calculation. This took something like 10 seconds on an 8-core AMD desktop. And it provides a very, very well-converged electronic density that we'll then use in the next step to calculate our orbitals on. So this is the salient piece of Nexus input. And then here's sort of the highlight of the output. If you've done everything correctly, then at the end of your first DFT calculation, which should be inside the runs/diamond/scf directory, you should have a file called scf.out. And you should see the following. You should see the total energy here is minus 22.749, blah, blah, blah. And this should converge fairly rapidly because this is an easy calculation. And as I said, this shouldn't take much time at all. It took 10 seconds on my personal desktop. Okay, now the second step is to take the density that we calculated in the first step using the SCF calculation to now do a non-self-consistent calculation for the supercell. Now there's a bit of sleight of hand going on here. I'm specifying that the system is called supercell, but this calculation is still done in the primitive cell. So Nexus understands that when you do this kind of a thing, what it really should be doing is using the primitive cell plus that very long list of K points that are required to tile whatever supercell you asked for with whatever K point grid you asked for. So don't confuse yourself here, even though this is not a typo, right? In other words, we are doing an NSCF calculation with a system set to supercell, but behind the scenes, Nexus is going to run this calculation still in the primitive cell, but with a huge list of K points, or at least a much larger list of K points than you would have in a corresponding supercell. Okay, and the reason to do this is that it's very, very fast to do these calculations. For example, both of these steps, the NSCF and then the subsequent wave function generation, which is the second green box down here, took like a total of like 3 seconds, 5 seconds, something like that. Again, on an 8-core AMD desktop. And what this allows you to do is like, you can write a loop in Python that will loop over supercell sizes, right? Or loop over K-point grids. And then you can very quickly and very easily do your K-point, twist grid convergence scans this way. So I like to do this sort of thing because it's very useful for doing sort of preliminary scouting missions, right? Where you can figure out how to outline the scope of the problem that you really want to tackle. You can very easily do your twist grid convergence. You can very easily see how many twists do I need for such and such a system, how much memory is that wave function going to take up, so on and so forth. So this is an idiomatic way to do wave function generation on crystalline materials. Now, this all goes out the window if you want to do something like a defect, or if you want to do an amorphous material, right? You don't have symmetry anymore. So you're kind of hosed if you want to do that. But for crystalline materials, this is the way to go. Okay, now at this point, you should have a file. Oops, let me go back one more. At this point, you should have a file called NSCF. This is in the runs/diamond directory /NSCF pwscf_output/pwscf.pwscf.h5. This object is a QMC pack wave function. So inside this object, as I mentioned in the earlier part of the tutorial, is a huge list of all the coefficients for the plane wave expansions of all the orbitals that you care about for all the K points that you care about. And so this wave function can grow very large. It can be multiple gigabytes if you're running in a very large supercell, hundreds of atoms. And if you're running with a large semi-core, a large number of semi-core states in the valence of your pseudopotential, these wave functions can be quite large. So this is also useful for figuring out, how big is the wave function going to be for my system that I care about. So, but at this point, if you've done everything correctly, you should have this file sitting here, and it should be a couple megabytes. I think it's like, maybe it was like 50 megabytes or something on my desktop. I can't remember exactly, but it's something like tens of megabytes. It's not huge because this is a small supercell with a small pseudopotential. And 4 electron pseudopotential. All right, now, if you've done everything correctly, you've got that wave function sitting there. And now the next step is to do wave function optimization using VMC. And so on the right-hand side, I'm highlighting for you the salient chunk of this Nexus script, solids_example.py. And here what we're doing is we're generating now a QMC pack input block called opt_j12. And as the name implies, this block is going to do 1 and 2 body Jastro optimization. So here we're specifying now doing the supercell. And again, there's a little bit of Nexus sleight of hand going on here, which is that Nexus now knows that, oh, you're doing a QMC calculation and I have an object that looks like a supercell. I better set up the input to actually run in the supercell. So Nexus is pretty smart. It can tell when you're doing a little DFT calculation to run in a primitive cell with K points, and it can tell when you're doing a QMC calculation that it should run in a supercell. Here, twist num equals 0. This is a very common idiom when you do Jastro optimization in a solid. I guess, in principle, the exact form of the Jastro might change a little bit with K, but like not statistically significantly for most problems, right? So a frequent approach is to just pick a twist, do all your Jastro optimizations at a particular twist, and then you just employ that Jastro for all twists, right? And so that's what we're doing here. We're saying, please don't run on that huge grid of K points that we gave you. Instead, please just run on the first twist, which is twist number 0. And the wave function that you should construct should include a 1-body Jastro, should also include a 2-body Jastro. I've listed explicitly the cutoffs for these 2 Jastros, which are both defined in real space. This happens to be the Wigner-Seitz radius of the 8-atom supercell. So if you change the supercell as you're playing around with this script by yourself, you should also plan to change these cutoffs. By the way, if you don't set these cutoffs, then by default, they will both be set to the Wigner-Seitz radius of the cell you're calculating. That's a little bit dangerous because what that will mean is that your 1 and 2 body Jastros, these spline forms of the 1 and 2 body Jastros, are not very transferable. So please be aware. I like to explicitly list the cutoffs for exactly this reason, because you can't just take a 2-body Jastro that's been optimized with a cutoff of 3.37, double the size of the cell, drop that Jastro in, set the cutoff to be twice as big, and expect that Jastro to work. It's going to be it's going to be a terrible, terrible Jastro. The variance of that wave function would be huge. You have to re-optimize it if you change the cutoff. So these Jastros are not transferable in that sense. So I always list the cutoffs explicitly, even though by default QMC pack will sort of do the right thing for you. Just because I'm a human and I forget things all the time, I always set those explicitly as a little reminder that I can't pick these up and put them anywhere I want. I kind of have to use them in place. The QMC method, of course, is opt. So this is going to be an optimization calculation. That means it's going to do VMC. And the min method we're using is called one shift only. It's a very robust algorithm. I would recommend that you pretty much only use this method, or at least you should use this one first. If you're doing something relatively mundane like Jastro optimization, this should basically never fail, unless you're doing something really silly like this Jastro transport business that I was just mentioning, right? Sometimes that can be a little pathological, but otherwise the one shift only method is very robust and it's fairly quick. You don't need a lot of cycles in order to converge in order to optimize a Jastro. Down here is just some QMC sort of guts that we're setting here. How many optimization cycles should we run? How many warm-up steps? How many blocks? What should the time step be? So on and so forth. Salient for these optimization calculations are these 2 flags, init minwalkers and minwalkers. This is basically the knob that controls how aggressive the optimization is. A lower value of minwalkers equals a more aggressive optimization. That is to say, bigger parameter changes in a particular optimization calculation, right? So a common idiom in what we're doing here is to do 3 or 4 cycles initially that are pretty aggressive. So you'll notice here I have init underscore cycles equal 4 with init underscore min walkers equal 0.01. So that's a relatively small value of min walkers, which means that the first 4 optimization cycles are going to be very aggressive. You can change the parameters in the Jastro a lot. And then frequently what will happen is you'll get a very rapid convergence to something that's almost optimal. And then we'll follow that up with 10 cycles with a much more, let's say, modest change in the wave function parameters here. So notice this min walkers is like an order of magnitude larger than a factor of 50 larger than in min walkers here, right? So the idea is you do a couple cycles at the beginning that are real aggressive, that'll get you pretty close to the optimal. Then you follow up with more cycles with small parameter changes. And what you should see is that the energy will fluctuate about some minimum value, right? It's QMC, so it's stochastic. So you're never gonna, you can't just look at the lowest energy and call it a day. You also have to look at the error bar, right? But this is kind of the idea. And this calculation may take quite a bit longer than the DFT calculations that you will have done up to this point. On my computer, which again is this 8-core AMD desktop, took about 5 minutes, but this could take much longer than that if you're running on a modest laptop. So I would just highlight that, general rules of thumb for Jastro optimization are: don't do too much at once. It's going to be difficult for you. And I think this question came up in the molecules example as well. Why can't you add in all the Jastros at once and do one mega optimization? Well, in principle, you can. QMC pack will let you do that. The problem is that, as you add more adjustable parameters to the wave functions, you need more samples to robustly optimize those parameters. And so that optimization can be very large. And, if your starting wave function guess is not particularly good, it can be rather difficult to converge for that optimization to give you a well-converged result. So a typical workflow for me is to first do a 1 and 2 body Jastro optimization up front, because you're pretty much always going to run with those. And then after I've optimized that, I tack on a 3-body Jastro and test to see if I get a reasonable improvement to the wave function or not. Is it worth paying for J3? And similarly for the k-space Jastro, if it's a modest or a small supercell, I'll do a test with the k-space Jastro and see, is it worth paying for a k-space Jastro? So as I said, this one shift method is what I would recommend. It's quite robust, and for Jastro optimization, it works very, very well. And regarding the cutoffs, all I would say is that the 1-body Jastro, it's pretty long range, it's sort of medium to long range. If you're running in an absolutely gargantuan supercell, you could probably start to truncate J1 without much change in the local energy or the variance of that wave function. But the 2-body Jastro is super duper long range. And so you should basically always set the cutoff for J2 to be as big as it could possibly be. Set it to be the Wigner-Seitz radius of the cell, because you will always get more. You will always get variance in energy reduction if you let J2 get bigger, right? As big as it could possibly be. And then, as I said, I think mentioned very briefly in the tutorial component, the 3-body Jastro is relatively short ranged, and it's very useful, or can be very useful, for improving the wave function of a atom with deep semi-core states in the valence, right? So for today, which we're doing diamond, which is just a 4-electron pseudopotential, adding a J3, basically no change, no statistically significant change in the variance or the local energy of that wave function. So we're not adding it here, although I've included an input block for you, which has been commented out underneath this one in the script. So if you just scroll down in the solids_example.py script, you should see a commented out region called opt_J3. And you'll see that it takes as input opt_J12. You'll see at the very bottom of that input block that says dependencies opt_J12, which means it will take the best wave function it found from opt_J12, take that wave function, slap a 3-body Jastro on it, and then do another optimization in which the parameters of J1, J2, and J3 will all be adjusted. Pardon me. So you can play with that if you like, and what you will discover is that adding a 3-body Jastro for this particular problem is sort of not worth the work, right? It does not give you a statistically significant improvement to the wave function. And as I said, I think in the multiple times in the tutorial component of this talk, the case-based piece of J2 is less important in larger supercells. This is an 8-atom supercell, which is really very small. So a case-based Jastro actually gives you a very significant improvement to the energy, which is to say a reduction, pardon me, pardon me. For this problem, adding a case-based Jastro gives a very significant reduction in the local energy and the variance of the wave function. However, I'm not sufficiently sophisticated with Nexus to figure out how to make it do a case-based input block. So I made you a case-based Jastro input block to play with. It's in the runs_diamond opt JK folder. So there you can look at what the J2 case-based Jastro piece looks like. And I would encourage you to run that optimization. I've already put in there an optimized 1 and 2 body Jastro. And so all that's new is the addition of the case-based Jastro. And you'll see is actually a very significant improvement in the wave function. And you also pay more, right? The block time goes up when you add a case-based Jastro as well. And you can adjust the cutoff of the case-based Jastro, and you can see how that will affect the results. There's a file in that folder, opt.jk, called, I think, notes.txt. And there I explain a little bit more about how to do that optimization, how to change things, what to change, and sort of what the improvement in the wave function looks like, what that reduction in the energy and the variance in the wave function look like. So what I want to leave you with in terms of wave function optimization for solids is that you should always, always, always use 1 and 2 body Jastros. And you should always test adding a 3 body and maybe a case-based Jastro as well. But always use 1 and 2 body Jastros. Okay, after you've optimized your wave function at the VMC level, now you've got a well-optimized wave function, you've got a 1 and a 2 body Jastro on there. Now it's time to do a production DMC calculation. And so you can see our final input block here called generate_QMC pack. Again, the system that we're running in is called Supercell. And the QMC, the calculation that we're doing, is now DMC. And we specify an initial VMC warm-up cycle. So first thing we do is we do a VMC calculation to move the walkers around, get a relatively reasonably well equilibrated set of walkers. And then we start the DMC. And you can see that our DMC calculation is going to be composed of 3 discrete time steps, starting at 0.02 and reducing by 2 for every subsequent time step. So the output of the DMC calculations will be one DMC calculation with tau equal 0.02, and then another calculation with tau equal 0.01, a factor of 2 reduction, and then a final DMC calculation with tau equal 0.005, another factor of 2 reduction. And you could see, again, this is the common QMC stuff that we're doing. By the way, I set steps equal to 1 on purpose. This is kind of a dopey thing to do. But I did this on purpose because if you were to graph using GNU plot, for example, what is contained in the scalar.dat file, the local energy in the scalar.dat file, you would see very clearly the equilibration, right? How long it takes for the DMC to equilibrate. And I like to do this actually, because I like to see that equilibration happen. Because then I can say, okay, look, I can very clearly see this thing, and it is equilibrated. Another strategy would be to take a gazillion steps in relatively few blocks, right? But I don't like to do that because I also like to histogram the scalar.dat, and I want to see that I have something that looks reasonably Gaussian, right? So my typical MO is to take fewer steps with more blocks. But no, there's kind of a trade-off. You can sort of do your own thing, and you should experiment and find out what you like to do. However, I would just mention that you pay a lot for blocks in terms of storage requirements, right? If you have a lot of estimators, the file size of the stat.h5 files writes an estimate for each of your estimators at every block. So if you run with like 5,000 blocks and you're running with like the spin density or the 1 RDM or n of k or some really heavy estimator, that that file, the stat.h5 file, one of which will be written for each series and one of which will be written for each twist, can be very, very large. So there's a practical limit sort of on what you can do, and you need to be aware of that. And this calculation should take substantially longer. It takes about 16 minutes per twist on my 8-core desktop. And I want to just mention one small technical detail. For the purposes of this lab, I'm running these twists in serial. You'll notice that I'm not showing it here, but in the script, I'm looping over the twists. So I say for TW in supercell.twists or whatever it is, right? And then I do in serial a DMC calculation on the current twist. QMC pack can run all of these twists in parallel, as I said earlier in the tutorial. It's just that doing this thing on a laptop is going to completely fry your laptop if you try to run them all at the same time. So I've included for you, again, commented out, I think above this portion, this code block in the solids_example.py file, what it would look like to run this QMC pack production calculation in parallel, like you would do on a really, a big supercomputer. And I've also prepared all of the input files in a directory called, I think it's called runs DMC parallel twists or something like that. And you can see that the input files are essentially exactly the same, except now there's an extra index that the files all carry around with them. And the input file, dmc.in, is now just a list of XML inputs. And so if you pass that to QMC pack is smart enough to look at all of those and say, oh, okay, I know what to do. I'll run all of these together at the same time. And it'll put one twist on, it'll distribute the twists over however many MPI processes you have. So you can see what that would look like, because that's probably what you'll be doing on a real supercomputer. But again, doing this on a laptop, I find, or even a desktop, frankly, I find is a little bit more tractable to do the twists in serial. So I think I'd like to just leave you with a few rules of thumb for DMC. Again, use VMC to seed the DMC, right? So we always do an initial VMC calculation to get ourselves a reasonably well equilibrated set of walkers to start the DMC from. I tend to prefer wide calculations over deep calculations. As I said, certain estimators can lead to huge files if you run with like thousands of blocks. So twists are cheap in that sense, right? If you know that you need 10,000 steps in order to achieve an error bar that you care about, well, you could run one twist for 10,000 steps, or 10,000 blocks rather, or you could run 100 twists for 100 blocks, right? And so doing it that way can be a little bit, that can make things a little more tractable. My time step strategy is to run for constant imaginary time. And so what that means is that and I think Nexus will do this for you by default. We don't specify it here, but I'm pretty sure if you check the input file, it'll actually adjust the number of steps. It will increase the number of steps by 2, a factor of 2, right? Because we're reducing the time step factor by a factor of 2. And so this is a common idiom, right? Basically, what you'll do is you'll say, I want to project out to the same amount of imaginary time in my DMC calculation. And so if my time step, if I decide, for example, that I need to project out to 0.1 inverse Hartree, then if my time step is 0.02, then I need to run 5 steps, right? But if my time step is 0.01, then I need to run 10 time steps. And if my time step is 0.005, then I need to run 20 time steps, and so on and so forth, right? So I'm pretty sure Nexus will do that for you. But that's a common idiom, and that's my approach as well, is to sort of figure out how much imaginary time you need to run for, and then you increase the number of steps as you reduce the time step factor. What this means is that the smallest time step takes most of the simulation time, most of the wall time, the human time is spent on that very last time step. So what you can do, I mean, the time required to do a calculation for a particular number of steps is the same. It does not depend on the time step. So what you can do is you can do some crappy calculations with a relatively small number of blocks with a relatively, whatever time step you want. And then you can figure out, well, how much time does it take per step? And then you use that to calculate how much wall time will it take for me to achieve a certain accuracy, wall time accuracy. And unfortunately, you just have to sit down and do that with like pen and paper or something. But that's my approach, right? Is I do a little calculation and I figure out like, okay, it takes one DMC step for the problem I care about, takes 30 real-time seconds on this many nodes of my favorite supercomputer, right? So I better, and I know that I need so many steps, so then I better, plan to run for this long in wall time. Right, generally speaking, you should always use more than 3 time steps. That's because you want to do a meaningful time step extrapolation, and so you want to fit a line, and so you want at least 3 points. And QMC is a big hammer. So when in doubt, add more twists. If you're still in doubt, run in a bigger cell. After all, flops are free, right? So with that, I think we're more or less done with what I wanted to outline for you in terms of the tutorial materials. And I'm happy to just hang out and answer questions if there are any, or other points of discussion if there are any.
Thanks very much, Josh. There's a few excellent questions in the chat. I'm going to, actually, there's more than probably we can go through right now, so I'm just going to pick what seem to be the most important and general ones. So first, a question from Rashid. Why are we doing a non-self-consistent field run after our self-consistent field run? We've got this sort of 2-stage strategy. Why are we doing that?
That's a great question. And I think the N in NSCF scares a lot of people because somehow you see that and you think not as good as SCF. But what we're doing here is breaking the DFT calculation that we use to generate the orbitals into 2 steps. The first step is a regular old SCF calculation, just like everybody is used to. And we do that calculation on a very, very large K-point grid. And then we store the density from that calculation. And so at the end of this step, what we have is a very well converged estimate of the electronic density for this system. Now remember, the potential in DFT depends on the density, right? So if we run an NSCF calculation, what it means is we take the density from the previous SCF calculation as input, and then we just say for this particular potential, what is my eigenfunction? What is my orbital, right? That's the NSCF. We don't then update the density. The reason to do this is because it's very often the case that you want like random K points in your supercell, or pardon me, there are like random looking K points that you will include in your primitive cell that you have to use in order to construct the supercell with whatever K point grid that you want. And so what you wouldn't want to do is to generate I'm speaking in general, of course you could construct an example where this would be okay, but generally speaking, what you don't want to do is do a one-shot DFT calculation on a relatively small number of K points and then write out the orbitals directly, because it's very possible that for that calculation, the density would not be well converged. And in that case, the orbitals would not be very well converged. And so breaking it into these 2 steps ensures that the result of step 1 is very good, independent of whatever kind of QMC wave function you want to generate. It also saves you a little bit of effort, although come on, it's QMC, so this is cheap anyways compared to the QMC, but it saves you a little bit of effort in the sense that you can use that density to generate multiple wave functions, right? So you're saving yourself a little bit of work. So you shouldn't be afraid of the N in NSCF in this case. It's not like we're doing a bad calculation. What we're doing is we're saying, I already have a very well converged electronic density. Please just go use that to calculate my orbitals, instead of trying to do it yourself on this particular set of K points that I happen to care about for my current problem. Does that help?
I think it does, Josh. And another a simple question, and that is, where could people see what the Wigner-Seitz radius is for the cells that they're running? You mentioned this sort of convenient trick of writing it down specifically in the input file. Does Quantum Espresso print that out?
Espresso does not. Well, so in general, you're going to do this calculation in a primitive cell. So I don't think Espresso will spit it out for you. But even if it did, of course, it's probably the Wigner-Seitz radius of the primitive cell. Honestly, you could calculate. I mean, if you look inside the supercell object, the supercell object knows what the supercell lattice vectors are. And you know everything there is to know about that supercell, or sorry, that object knows everything there is to know about that supercell. So you could calculate it yourself, given the contents of supercell. But I'm very lazy. So what I do is I just run QMC pack real quick, and QMC pack will spit it out right in the top of the output file. It'll tell you, here's my Wigner-Seitz radius. And so I frequently will just do that, and then I'll go back and I'll manually hack it in.
Thanks, Josh. Another question about selection of Jastrow factors. This is from Roman. Is a 3-body Jastrow factor necessary for heavier elements, or are we good with just a 1- and 2-body Jastrow?
The answer is to test that for yourself, but generally speaking, that is to say, you should always test these kinds of things for yourself. And the optimization calculations are relatively lightweight when it comes to QMC. Like, that is not the bottleneck, right? Your wave function optimization is not what's going to eat up the bulk of your supercomputing time allotment. It's the production DMC that's going to eat all that up. So by all means, you should test that if you are concerned about whether you need a 3-body Jastrow. But rule of thumb is the 3-body Jastrow is very useful, or can be very useful, can be very important, is worth using in the case where you have deep semi-core states in the pseudopotential, right? So if I had I'm trying to think of a good example. Let's take magnesium, right? 2 kinds of flavors of magnesium pseudopotential you could think of, right? One would be a 2-electron pseudopotential for magnesium, and another would be like an 8 or a 10-electron pseudopotential for magnesium, right? You could have like a helium core or a neon core, I think it is, for magnesium, right? I would bet you that the 3-body Jastrow won't give you much for the 2-electron pseudopotential for magnesium, but I would bet you that that 3-body would really pay off if you had a big fat 10-electron pseudopotential with those deep 3s states floating around in there. So the answer is to always test if you suspect that, or if you're curious whether something is going to be worth it.
I notice we're just past the hour boundary, so this will be the last question. This is from Ilka. Can QMCA combine the serial twist data straightforwardly, for example, when calculating the twist average total energy?
Yes, it can. And I actually forgot to show that. So that's a great question, Ilka. Thank you. So here's a sample output of what my DMC data looks like. Of course, the exact value of your data will be different because it's QMC and it's stochastic, but they should be statistically very similar, very comparable. And so here are each of the twists. You can see I'm running them in different directories, TW0 to TW3. So here it all is in QMCA. And then if you look inside the supercell object, again, it knows what the K-point mesh is in the supercell, and it knows what the corresponding supercell, or K-point weights are in the supercell. And so you can use QMCA to do the twist averaging with the weights for you, and you obtain the following kind of results here. So the answer is yes, you don't have to write any extra code in order to get twist averaged results from these kinds of calculations.